Hello everyone, welcome to ACE's Premium Tutoring Service. My name is Andy. Welcome to our week's video. I know it's been quite a while since I have posted anything, but I had a few tutoring appointments today, and a lot of people were really struggling with use substitution, so I decided that I was going to post a video, just try to clear up a few of the issues that people weren't quite understanding. So, the reason that we use substitution is when we have an integral of f of x and it's too complicated. We don't have the ability to integrate it. We look at it and we think, what function has this as its derivative, and just we can't see it. So we want to find a way around. So our normal path is not working, that we can't just find the integral. So what we're going to do is we're going to change the variable, integrate in a more simple variable context, and then change the variable back. So we're going to work around what we can't do to get an answer. Okay, so let's take a quick look at an example for use substitution. So just looking at this one, you say, hey, what's the integral? I have no idea. Okay, it's not something I know how to do looking at it right now. I don't know what function has this as its derivative. But if I use the techniques of use substitution, maybe I can create a simpler problem, solve it, and then use that to find the answer. So one of the trickiest parts about use substitution is picking the right u. It's first of all something that just comes with practice, and second of all, if you've chosen the wrong u, it will become apparent pretty quickly because your problem will be getting harder instead of easier. So you can always go back and choose a different u if you're not making any progress. One of the keys to picking a u is that you want your u to be chosen such that your du gets rid of part of the problem that's making it so tricky. So you see what I did there? I chose u to be ln of x. I know the derivative of ln is 1 over x, so my du gets rid of this x down here. It works out perfectly, and a lot of the times that you're using use substitution, especially in M119, the problems will be set up so that the derivative of one piece will cancel out another piece of the question. So it's also very important to carry in this dx when you do this derivative, so that you can, when you're plugging in all of these pieces, that everything gets taken care of. So we're going to change the variables here. Instead of ln of x, we're now going to say u, and it's going to be cubed. And then we have 1 over x dx here, and we're going to say that 1 over x dx is our du. So we're taking the integral of u cubed du. Now, I know the antiderivative of any power. You're going to increase the power by 1 and divide by that number. And add a c. So now we have created a simpler integral, solved it, and now we're just going to find an answer in terms of x, that you always want your answer to be in the same variable that you started with. So if you have an answer that's in terms of u, you're not done yet. So this is almost there. We know that u equals ln of x, so I have ln of x to the 4th over 4 plus c. So what's the integral of ln of x cubed over x? ln of x to the 4th over 4 plus c. I would not have known that just by looking at it, but it's simply done. Okay, one more thing I want to talk about with use substitution is a definite integral. And when you're working with a definite integral, there's a little bit difference in technique versus an indefinite integral. And that has to do with the fact that you're looking for a numerical answer. So there's no need to go all the way back to get an answer in terms of x, that you can use a little bit of a shortcut, which I will show you now. So I'm looking at this problem, and I've identified it as a u substitution problem. I'm going to set my u equal to this inner part, x squared plus 3. The reason I do that, oftentimes you'll find that one of your parts is of a degree 1 more than another part. So often that will be your u. So as you see, when I do my derivative calculation, I get a 2x dx. What I'm looking for is an x dx. That's what I have in my equation. So I'll divide by 2 here. So I have du over 2 equals x dx. Now, there's one more piece to the puzzle in order to create an integral that's entirely in terms of u. So right now, we're integrating from x equals 0 to x equals 2. Now I have a function that gives me u for any x. So let's say that instead, I'm going to integrate from u equals 0 squared plus 3, so 3, to 2 squared plus 3, which is 7. So I'm going to integrate from u equals 3 to u equals 7 of 1/2 u cubed du. Right? So I changed my x's to u's, I changed my dx's to du's, and I changed my limits of integration from x's to u's. So now I've created an entirely new problem in an entirely new variable that will give me the exact same numerical answer as the question that I started out with. However, you can see that this one is much easier to solve. So I know that the antiderivative of u cubed is 1/4 u to the 4th. 1/2 of that is 1/8 u to the 4th. I'm going to evaluate it between 3 and 7. I don't know 7 off the top of my head, but I know that this will be 1/8 7 to the 4th minus 81. Okay, so I hope this was a helpful video. I hope everyone understands u substitution a little bit better. If you need more help, I'm on Facebook at facebook.com/acestutoring and also at acespremiumtutoringservice.com. Thanks for watching.